Okay, we're starting with the partial contract that I'm going to supply you with. And I'm going to start adding pieces to it and walking you through things in the language. So the first thing is up at the top. Basically, these days you have to have this formatted thing indicating the license. I have picked the MIT license for the stuff for this class, but you don't have to stick with that. You can change the license to whatever you want, but it has to be some sort of a license where I can actually read your code. Pragma specifies the version of the compiler. And I've said anything less than version 9 of the compiler. We're using version 8. The default that's installed with Truffle, I think, is version 5.6. So in the Truffle configuration, I've actually specified that it has to use the version 8 compiler. It will go out and pull in that compiler when you do your first compile, which you've probably done by this point. Everything is either a contract or a library in Solidity. We're doing a contract. If this inherited from other contracts, it would say employee vest is on some list of multiple inheritance. One of those things in Solidity is that you have to, if you're going to have multiple inheritance, put all of your multiple inheritance things in the same order. If you don't, you will get bad results, and it will not tell you. You will have to find that during testing. But order is important. We're not inheriting from anything. So Solidity has structures, and there's a variety of data types. Let's talk about the data types for a second first. There's strings. There are integers. We can go over here. I'll put the link into this for tutorials point. They have a nice documentation on the types, but the base types are like booleans, integers, and fixed point numbers. And the booleans, integers, and fixed point numbers, pretty much I'm using things that are either a boolean, a int, or an unsigned int. And you'll notice that the integer is int 8 to int 256. And the unsigned is the same. It goes 8 to 256. So if you really want a 48-bit integer, you can do int 48. This means that there is every data type in there from 8 bits to 256 bits. And if you do conversions between them, there are conversion rules for all the different data types. You'll notice that nowhere in here is there any floating point or decimal value type things. These are all fixed point, and basically they sit on top of integers. So when we do a percentage, what we're going to use is we're going to use a uint256, which is way big, and we're going to multiply the percentage by 1 million. And then we're going to do our own calculations inside the contract to make certain that when we do truncation and we divide by 1 million to get a value, that we do the divide last. So we multiply and add first and divide last so that we truncate after we have bigger values. We're also going to be doing that with unsigned, not signed numbers. So you can't have a negative percentage. And we do have to be very careful with how we do calculations. Now, in here we also have stuff like structs, which it gives you in this documentation a nice thing on. Here's struct names and types. It has a string data type, and there is also a byte data type. Bytes are way more efficient than strings. A string stores each character in a 256-bit integer, which is not real efficient in some contexts. That happens in the binary interface for the language, which is how it's called. Bytes are stored differently and tend to be more efficient, but if you want something to behave like a string, then you're going to have to use a string, whereas, a byte array is more suitable for binary data. And it does have other things besides structs. There are arrays. At some point, we're going to want to add to this, as a part of the homework, a way of getting our employees and listing out the entire set of employees. Now, I've declared an owner address, which I'm going to use in the contract to determine when the owner is accessing the contract. That's the person that can grant, create new users, stuff like that. That's a permissions thing that we're going to implement. The number of tokens that the business is creating. So if you have 10 million tokens and you're getting 0.25% of that, then that's 25,000 tokens when you're fully vested. The way vesting works is if you stay with the company for long enough, in this case 4 years, then at the end of that period you are considered fully vested and you get the entire amount. So at that point you would get the 25,000 shares transferred to you, or the 25,000 tokens. Before that point you may be partially vested and have a percentage, but that percentage may not be granted, as in if you leave the company you lose it. So that's the model that we're going to work on. And the number of days to vest is my calculation for how many days there are in the 4 years, or say you do a 3-year vest. That's the number of days that are required to vest, which in this case is 365 times 4 plus 1, which may not be accurate all of the time, but most of the time works with leap years. Now, Solidity has hashes where you can map from one ad type to another. In this case, I'm going to go from the address, which is the employee's account address, to the employee. And it's internal. You can't access that from outside, so you can't pull out this number with just a call to the contract to say, is this a public value? Let me see what it is. This information is internal and hidden, and we're calling it vesting. Now, one of those interesting things about Solidity is that Solidity doesn't have a way to iterate across a map. So for us to be able to actually pull back the list of employees means that we're going to have to keep separate data as an array and keep that in conjunction with the map so that we have a list of keys for the map. And the way we will do that is we will say that I want to have address, and it's an array, and vesting, we'll call it vest list. And that vest list is going to end up being populated with each of the addresses of employees. But this also means that if we delete an employee, if they leave the company for some reason, that we have to go back in and do something with that address. In our case, we're not going to build it so we don't have to do much. But it means that every employee that leaves will still have a record of them in this vesting list. So it'll be a simple way to implement it. But if we actually had to delete people, the only way to delete from the array would be to actually go in and recopy the remaining values in the array to previous positions and put an empty value into the array. We can't actually shrink the array. And that recopy operation is extremely expensive, since every time we copy something, it means that we're going to have to pay the cost in gas for running the contract of that write for that copy, and then you go down the next one and you copy the next one. So that can be very expensive. Another way to delete stuff would be to just take the deleted entry and set that particular thing to some marked value. When we talk about things being stored, something like address list or days to vest, each one of these things is in the most expensive class of storage in Ethereum. That's what we'd call permanent database storage. And you pay a good deal of gas for that storage. A cheaper alternative for having things stored is to create an event in the transaction. And that's what these events declare, is that you're giving it a name. You're saying that it will also be addressable by the index that's used. And then it has some parameters like name and start date. So these things are things that when we emit these events, we can write them into the transactions, and these can then be searched efficiently in the transactions. Solidity has an interesting construct for adding additional constraints on functions. And that's these modifiers. In this case, this modifier only owner says that to run this function, you have to be the owner. And if you're not the owner, if the message sender, the one making the transaction request, is not the same as this owner address, this is this variable up here that we've created, you raise an exception and it returns this message. Fortunately, they finally made it so that the messages actually return to the user. That's a fairly new thing in Ethereum. And how do we get the owner address? That's down here in the constructor. The constructor runs when the contract is created. That's when it constructs its data. One of the interesting things about these contract objects is that they run over time by different people. And the constructor is run by the person who creates the contract at the time when the contract gets created. It's in that transaction. So the message sender, the one who created the transaction to load the contract, is the owner of the contract. And if we save that for later, then we can turn around and use this only owner modifier that we've created to say, yeah, the new person in the future that is the message sender, that person, is that the same as the person who created the contract? So we can use that to create a level of security in contracts and permissions that say that, yes, this is the one who created the contract, you are the owner. If the contract receives funds, say it's selling something, then the owner of the contract is the one who should be able to disperse and transfer those funds. If the contract represents tokens for a business, essentially the stock for a business, then who can decide to create more stock or to destroy existing stock, to render it non-existent? Well, the owner of the contract, who is the owner of the business. So that's an important level of security. The other things that the constructor is doing is it's taking this parameter, the number of tokens that are created, and the days to vest, and calculating out those. You'll notice that I take days to vest if it's 0, and I set it to a default, which is roughly 4 years. So that's kind of pieces that I'm giving you in terms of this contract. And this function get days to vest just returns a value. So let's do start vest. Start vest is what you do when you hire a new employee, and on that day you're going to say, yes, we want to set this employee up to start vesting. So on the day that it happens, which means we're going to use the current time as the start time for that employee. There's another function about after here that lets you set a start vest with a date in the future or past. Like the person is going to start next week, and I want to set the date to that date. Dates are integers in the Ethereum system. They're basically the number of seconds since 1970, which matches with a Unix timestamp. And that's also how dates are stored in the transaction blocks. Now, if you think about a block, you have part of that block created when smart contracts run, and then there's other things that after the smart contracts run, like the seal on the block, that gets created. So the beginning time of the block is the current date that is available inside the contract. It's not a time like a wall clock time. This is the time for this block to run. And that time is universal across the entire network, as in they all have the same start time information for the block. One last note on the package before we get started actually building Start Vest is you'll notice that this contract is called Employee Vest. And you have to put this in the employeevest.sol file with the same capitalization, or other things like migration and testing will break with error messages that have no meaning to reality and what the problem is. So if you get one of these messages about unable to initialize, what it's complaining about is that your file name didn't match your contract name. That also means you can only put one contract in each file. And I haven't found this anywhere in the documentation, but if you're working with a system that is case insensitive, like Windows file system or Macintosh file system, Remember that your employee vest has to have the same capitalization, the file name, without spaces as that contract name. So even though you may be able to create a file and the file system is case insensitive, Solidity and its testing system are most definitely case sensitive.